Finally, we're going to finish up this section of light. Notice it's a lot of material on this particular day, talking about thermal radiation and the Doppler effect. So when we talk about thermal radiation, we're really sort of focusing in on the continuous spectra, which remember is all the wavelengths are represented. It looks like the rainbow. Those are going to be produced by an opaque object, which means a dense object we can't see through, which is heated and releasing light. So this could be a hot dense gas, a hot heated liquid, or a hot heated solid. We say that that's thermal radiation. And so we want to look at the different qualities that depend on the temperature. So we know that as we heat up this poker, it's going to go from sort of a dull red to an orange to white hot, if we could get it that hot. So that's the first relationship we're interested in, and it has to do with what we call these thermal radiation curves, which I also had a short video on. And basically, these three curves right here, notice, are for different temperature objects, with the top curve being the hottest object and the lowest curve, well, the human, being down here. But notice there's two things that we want to notice. The curve in general gets higher and covers a wider range of wavelengths as the temperature gets higher. But we also notice that the peak shifts to shorter wavelengths. That shift to the shorter wavelengths is what we refer to as Wien's law. Here, this term, this little notation you might recognize from your book. This is the Greek letter lambda, which represents wavelength. Lambda max means the wavelength where the peak of the curve is occurring is related to a number, 2,900,000, divided by the temperature. So what it means is the temperature goes up, the wavelength where the peak occurs gets shorter and shorter. And that's what we saw in the past slide. Stefan's law refers to the fact as the temperature goes up, this whole peak gets higher and higher. This summary of three types of spectra was covered in another video, so I'm not going to explain it again. The Doppler effect, finally, is the effect that we hear. Usually we're familiar with it for sound, of how the pitch of something changes as an object approaches or goes away from us. I'm going to go back to this slide and actually see if this works. So that's the Doppler effect for the horn blowing. As it's coming towards us, you hear the pitch get a little higher, and then it sort of seems to trail off and it gets a little lower as we go away. And so that's what we're talking about. If the source of our sound was stationary, it wouldn't matter where we stood. We would hear the same pitch, which actually refers to frequency, and it would have the same wavelength. But what happens when the source of light is moving, what happens is in the direction of motion, the wavelengths get all compressed, which means that the frequency gets shorter. And in the way when it's moving away from someone, that actually lengthens the wavelengths and the pitch actually gets lower. So the reason that that horn sounded weird is that as it was coming towards us, or whoever was recording the sound, the wavelengths were getting shorter, the frequency was getting higher, and so it went up in pitch. And then as it moved away, when the wavelengths were getting longer, the pitch went down. It turns out that because light can be described as a wave, the same thing happens when we have a moving source of light. When we see it moving towards us, because the wavelengths get shorter, we say that they're going towards the blue end of the spectrum. So a light source shifts towards the blue, and we call that a blue shift. It's moving towards us. If the light source is moving away from us and the wavelengths are getting longer, we say they're moving towards the red end of the spectrum, and we call that a red shift. And so here are some different pictures showing, here's what the spectrum is supposed to look like. Here, you know that the object must be moving away because it's shifting towards the red. This shift here is even more, so what that means is it's moving faster away from us. This down here is shifted towards the blue, and so that means that it's moving towards us. This is shifted even more, and so it's moving towards us even faster. What happens is we can get different things of information when we look at something and it's Doppler shifted. We can see if it's moving towards us or away from us. The one problem is if the motion is exactly perpendicular to us, we don't see that motion. We only see the motion as it is along the line between the source of the light and the Earth. And for this picture right here, this star is moving a little bit away from us, but also sort of perpendicular to the Earth. So we can only really infer the motion away from us. We can't really talk at all about this motion in the line perpendicular to us. We can also see some things in the Doppler shift for rotation as well, but you can read about that in the book.